in a real difficult course versus making 95% in a soft A in a gimme course, you're doing a hell of a lot better in the difficult course. You're not getting anything from the soft course other than a grade which doesn't mean a damn thing because it does not reflect any true learning. I don't do that. This place is for learning. And although I can't control what takes place out of the boundary conditions of my class, in my class, we are going to do everything we can to get it learning. That's why I do what I do. That's why I build in all the earnable extra credit. It's entirely possible for folks to make an A in this gathering without even taking the last exam. It has happened. It's there. Now then, on with chemistry. We have finished analyzing aqueous solutions of Bronsted Lowry acid and bases, where the acid solute is monoprotic. Practically speaking. Like HCl. Per molecule of HCl, you can only get one H+. Same for bases we have so far considered. Now let's take a look at a somewhat more complicated issue, and that corresponds to the possibility of the parent acid, under appropriate conditions, being able to donate more than one H+. Most common example of such is sulfuric acid molecule. Sulfuric acid molecule is molecular and strong. Or the parent acid might be polyprotic, molecular and weak. If you look at the acid-base table, you'll see a number of examples of such acids. H2S is probably the simplest one formula-wise. Hydrated CO2, there's a bunch of other ones on there. Phosphoric acid is triprotic. Oxalic acid, which you may not know by the name, but you'll see by the formula, HO2CCO2H. I asked you about that on the exam. The anion of oxalic. A lot of examples. Or the one type of acid we have so far looked at, but not from a polyprotic activity standpoint, hydrated metal ion. So, we'll see there's a good deal of variation in the chemistry shown by these three different types of polyprotic acids. Our analysis will show us why. We start with sulfuric acid. Parent acid is molecular but strong. And ask the question, for 1,000th molar sulfuric acid solution, could we well expect each original sulfuric acid molecule to possibly lose 2 H pluses per molecule? If so, why? Why, under these concentration conditions, could we expect per molecule of this we might well get 2 protons? Well, here's the chemistry. If the second proton is lost by the parent acid, it's really coming from hydrogen sulfate ion, which is produced by this first reaction. What's Ka for hydrogen sulfate ion? 1.2 times 10 to minus 2. That's on the acid-base table. And from conversation we had last time, if Ka is a value that's bigger than 1 times 10 to minus 7, did I ask you about this on the exam? You betcha. If K is bigger than 1 times 10 to minus 7, the acid, as a consequence of dilution, can react to an extent which exceeds 50%. Well, 1.2 times 10 to minus 2 is a hell of a lot bigger than 1 times 10 to minus 7. Which means under fairly dilute conditions, we can well expect hydrogen sulfate ion to lose H plus by this reaction. which in sum means that each original sulfuric acid molecule winds up losing 2 H pluses. Why? Again, because Ka for this acid is a lot bigger than 10 to the minus 7, and this is a fairly dilute solution. You remember what ionization extent depends on? The magnitude of Ka and the dilution factor. 1 over m sub I. Hey, we already did that part. All right, so look at this first reaction. As a reminder, what's the extent of this? How large? 100%. Well, what's that tell us? I wrote it here. This tells us that the hydronium ion concentration for any sulfuric acid solution cannot be smaller than the numerical label on the bottle. If it's 6 molar sulfuric acid solution, hydronium ion concentration got to be at least 6 molar, because that reaction goes 100%. Okay? Now let's look at the second reaction, where hydrogen sulfate ion is perhaps also contributing to the solution hydronium ion concentration. Extent? Well, the extent we don't know. We'll have to determine it. But we already have reason to expect that it can be high, because Ka for hydrogen sulfate ion, again, is 1.2 times 10 to the minus 2, which is a lot bigger than 1 times 10 to the minus 7. And this is a fairly dilute solution. But since this is an equilibrium reaction, we'll write this. Now then, what do we get from the second reaction? The ionization of hydrogen sulfate ion. We get the fact that the hydronium ion molarity is the sum of m sub I, the label on the bottle, plus the sulfate ion concentration. Do you see this? Let's play a game. Let's imagine I make a solution in which I put 100 sulfuric acid molecules. The concentration of the solution cannot be known unless they tell you how much water we dissolve these in. That's immaterial and irrelevant. 100 sulfuric acid molecules. After the first reaction goes, how many of these do we have left?
0.
How many of these do we have? How many of these do we have? That's after the first reaction. Okay? Now let's take a look at the second reaction. This starts out at how many? 100. And we know that the sum of these molarities has got to be what? For this system. If this doesn't go anyplace, this stays as 100. If this goes 100%, this goes 0, and this becomes 100. You agree with that? So, somebody pick me a percent for the second reaction. Something between 0 and 100%. 30%. All right? If this goes 30%, 30% of these got converted to those. All right? So after the second reaction goes on a 30% ionization extent basis, how many of these do I have? 30. How many of these do I have? 100 minus 30, right? So that shows me this plus this equals what? Equals this. Okay? Isn't that the label on the bottle? And now, how many of these do I have? I made 100 by the first reaction and 30 more by the second reaction, didn't I? There you go. That shows this. Nothing fancy about this if you pay attention to the chemistry. So, we showed this, and we also showed this, pardon me. So it follows that the hydronium ion concentration in any sulfuric acid solution is equal to the sum of m sub I plus the sulfate ion molarity, or if you wish to express it in different fashion, it's the hydrogen sulfate ion molarity plus twice the sulfate ion molarity. You see that? Isn't m sub I equal to this plus this? Well, here's M sub I. So I'll write in hydrogen sulfate ion molarity plus sulfate ion molarity and add them up. That gives me that. Now I know the problem that a lot of you folks have. It's the algebra course problem that I described to you. Remember that? When I told you how my class took a test and every unknown was X and Y, and the other class took a test and every unknown was A and B, and they flunked? There's no reason to flunk. But the same thing will happen to you if you look at this and say, oh, these chemical formulas, what the hell do they mean? Nothing unusual. If you put in X and Y, you'll see this at a glance. Well, I don't want X's and Y's, because then you lose sight of what X and Y mean chemically. So I don't want you to do that. So if you write it out like this, you won't lose sight of the chemistry. I admit, you'll use up more graphite, too bad. You'll spend more ink, too bad. You'll use up paper at a faster rate, too bad. If those are your concerns, then you shouldn't be here. All right? Wonderful. Now then, with this having been established, we can, for this solution, I mean in this case, the 1,000 molar sulfuric acid solution, get at solving for the hydronium ion concentration. We'll put this as 3. Thus, to solve for H3O plus, for HO2SO2 solution, of course water is the solvent, we must consider, or what? What do we got to consider? That's a given.
Ionization extent.
And how do we get at ionization extent? We got to pay attention to this reaction, don't we? So what we got to consider is the equilibrium constant expression that corresponds to what? Ka for HOSO3 minus, don't we? So I'll write ionization EQ for this in terms of this. We've now laid it on the line. Everything you've got to pay attention to in order to be able to analyze in detail, to whatever extent necessary, a sulfuric acid solution, with water being the solvent. So here we go. There's Ka. I'll condense my formula for hydrogen sulfate ion. And here is the equilibrium constant expression, written properly as a chemical expression. If you go from this to something in terms of X's and Y's, you are inviting disaster. For example, if you write 1.2 times 10 to the minus 2 for your sulfuric acid solution and write X squared over M sub I minus X, what happens? What happens? What happens regarding the number of points you're going to earn for this question? It goes to what value? 0. So that doesn't apply to this. You got 2 sources of hydronium ion, right? If you forget the chemistry, game is over. That's it. But if you keep in mind the chemistry, then you can win the game. And that's what we want. Now, for this sulfuric acid solution, let's write 0.00 10 plus sulfate ion. This is sulfate ion. Wish they took the thing out of there. There. Now, what would you like to write down here instead of the hydrogen sulfate ion molarity? Tell me. You know.
MI minus
What's MI?
0.0010.
Like that? How many unknowns we got now? Can we solve it? You're daggone right. How are we going to solve it? What's our method? Brood algebra? Phooey, nuts, never. Now, when you do exams, or quizzes if we give them, I can't hover over you like a guardian spirit and see exactly what you do when it comes to the solving time. But I believe you me, if I could, I would. And if somebody would, for example, reach for the quadratic formula, because if you expand this, it'll become a quadratic. Whack! And I'd break your calculator. Put up with that stuff. Because you don't learn if you do that. And we want learning. How have we attempted to program you to solve expressions like this? What's the consideration we asked you to make? Speculate on percent ionization. How about that? You betcha. And what should we always try first? 50%. Why should we try 50% first?
If it's higher than 50%.
Well, I understand it's going to tell us that. If we try 50% ionization, what does this become? Oh no. It's Ka, game's over. Because when the sulfate ion molarity is such that this term equals this, game's done. We got it. %% ionization. This is half of M sub I. 50% ionization. This is half of M sub I. Right? So at 50% ionization, let's write this up here. This term is M sub I plus half of M sub I. Hey, that's pretty easy. So at 50% ionization, this becomes 0.0015. How's that compare to this? Is that bigger or smaller than this? Let's rewrite this in scientific notation, 1.5. I know you folks need practice, because I notice, whenever you folks deal with whole numbers, you're okay. But as soon as I put in a decimal point, the sparks start to fly. As soon as I talk about a fraction, troubles happen. I don't know what the heck's going on in grade school and high school math classes these days, but what's going on is bad. It's bad. Because you folks short circuit when you see decimal points. And that's not your fault. Now, you don't have the time and wherewithal to go back to high school or grade school and fix this. You got to fix it now. Scientific notation is 1.5 times 10 to minus 3. Now, a number of you, when I asked you, how does this compare to this, you told me that's bigger. Come on. That's no good. You got to let these numbers talk to you. When you see these numbers, you got to read them in your mind and ask yourself, what does this mean? That's the way the number talks to you. And that way you'll get rid of this decimal point fear or whatever it is. You got to do it for your benefit. It's not difficult. The problem you have is lack of familiarity. You haven't been doing it. But do it. Do it with the very best calculator you got. This thing. So what do we know now for this solution? The true ionization extent compares how to 50%? Thus, true percent ionization greater than 50%. Hey, you know what to do now. You can do the arithmetic. It's about 90%. Let me see what it is. I got it written here someplace. Uh, 87%. And again, you know, at this point you're doing arithmetic. We've done all the chemistry. So you do the arithmetic if it's necessary. All right, let's try 1848. Over there. (1848) is a question which I wrote so that you can recognize how a sulfuric acid solution talks to you as a consequence of large versus small m sub I. Large m sub I is concentrated sulfuric acid solution. Small m sub I is dilute sulfuric acid solution. Now I know, I'm betting, that what's going on in your mind right now is, what the hell does he mean when he says large? What the hell does he mean when he says small? And those are very fair questions. What do you think now, from a chemistry student perspective, corresponds to a large concentration? Everybody got a number in their mind? One significant figure number. Something that's equal to or bigger than 1 molar. 10 molar. 10th molar. 100th molar. Nobody got any numbers? Practically speaking, I'll give you my definition from a chemistry perspective. Fairly concentrated is on the order of 10th molar or bigger. Fairly dilute, 1000th molar or smaller, 100th molar or smaller. So you got a gray gap in there. What am I going to say 0.01 to 0.1? Well, what? I'm not going to say anything. Because when you talk about solutions of that molarity, and you want to know about ionization extents and things like that, you got to pay attention to Ka values. You can't escape from it. Like you said, there's no more of this, let's take a recipe and shove numbers into it like you did in 2045. Here you got to be thinking all the time, on your toes all the time. I mean, I'm telling you what's real. If there was some simple recipe you could take this stuff and put it into, hey, I'd be glad to share it with you. Now then, very concentrated sulfuric acid solution. Well, let's pay attention to these reactions. If it's very concentrated sulfuric acid solution, what would you say first about the hydronium ion concentration? Small or large? Large. Very concentrated sulfuric acid solution. That means the hydronium ion concentration has got to be large. What are you going to say about the hydrogen sulfate ion concentration? Large. Well then, by default, what are you going to say about the sulfate ion concentration? Very concentrated sulfuric acid solution. Let's put it this way. This is going to be about the same? Will this be a whole lot bigger than this? Will this be a whole lot bigger than this? I've given you 3 possibilities. For which one do you vote? Keeping in mind, of course, that if you don't defend the vote, you get nothing for the vote. Not any. 0 zip. All right, I'll tell you the answer. Why is this true?
Because the larger the concentration, the less the ionization extent.
Yeah! Remember what we programmed you with? Hey, very concentrated solution. This thing isn't going very far. Okay? Now let's then recognize that for any such solution, the hydronium ion concentration is also much greater than sulfate ion concentration. Okay, now let's talk about the very dilute solution. Here's V conc. We're going to talk about sulfuric acid solution. Here's V dilute. V large, V small.
Large. Be large.
This is a very dilute solution. That's okay. You've got to learn to let this stuff talk to you. You've got to know what it means. If I've got 10,000th molar sulfuric acid solution, the hydronium ion concentration it's twice that value. But that ain't a big value. Okay? Now then, let's go to these two. First of all, can these possibly be large? You can't get something for nothing. They can't be large. But how do they compare? And how do these compare? V dilute. Well, if it's V dilute, what kind of ionization extent we got for this thing? Daggone large. So how are these going to compare?
That's what we're later.
And now we turn the tables. Okay? And how will these compare? Twice. I'll write down twice. Come on, make a statement.
SO4 is going to be 2 times. Actually, no. H3O plus is going to be 2 times bigger than SO4 2 minus?
You betcha. Because practically speaking, now the second reaction is going 100%. If it's quite dilute. Well then, remember what we had here? From the first reaction we get hydronium ion. Second reaction we get hydronium ion and an equal mole quantity of sulfate ion from the second reaction. Total hydronium ion, what you get from the first plus what you get from the second. So in this case, hydronium ion molarity is going to be twice the sulfate ion molarity. Now then, watch out. V-conc, V-dilute. In V-conc, this condition exists between these species. And in V-dilute, this condition exists between these same species, okay? In which solution is the sulfate ion molarity greater?
V-conc.
We got to vote for V-conc. I'm listening for any seconders or anti-supporters who are going to vote V-dilute. Anybody voting V-dilute? How could it be more conc in V-dilute? Yeah. Sulfate ion concentration is greater here than it is here. Okay? Wonderful. If you don't see it, do some arithmetic. You'll see it. Now let's take a look at 1849. Now we're going to give you a condition. We're going to say that for a particular sulfuric acid solution, this concentration relationship exists. If that be true, what is the hydronium ion molarity? How do we get it? Well, we know we're going to have to do this someplace along the line. I mean, consider this someplace along the line. That's for sure. All right. Now, with this information before us, since we've already wrested this information from these two pieces of chemistry, can we turn this into an equation where we have one unknown only? You're daggone right we can. How do we do it? Well, let's write this. And for this solution, we said the hydronium ion molarity relates how to this stuff? Four times that one, right? So if we wanted to know such, we have recognized that for this solution, this condition exists. And if for sulfate molarities, wait a minute. Yeah, okay. Equals the hydrogen sulfate ion molarity plus twice the sulfate ion molarity. You believe that? Isn't hydronium ion the same as 4 times the molarity of sulfate ion? So put that in here. So I got 4 sulfate ion molarities equals this plus this. So how does this relate to this? It's all right? Nothing fancy about this. I repeat, if you have difficulty seeing this, the difficulty arises from the fact that these are chemical formulas rather than A's and B's and X's and Y's, the likes of which you see in algebra class. Well, don't put in the A's and B's and the X's and Y's, because the chemistry part will go up in smoke. At least it may well do that. Okay? Well then, if this is 2 sulfates, I can put in 2 sulfates, and if this is 4 sulfates, I can put in 4 sulfates, and then sulfate over 2 sulfates becomes 4 sulfates over 2 becomes 2 sulfates, doesn't it? So sulfate is half of this. Take it from there. Hey, arithmetic now. You know what to do. On we go. Keep in mind now, we're at the point of, for this problem, we've done the chemistry. We've done the algebra. Only thing that remains is arithmetic. You got to do that part. Okay? So we go to case 2. Parent polyprotic acid is weak and molecular. The one we just looked at, the parent acid, was strong, but molecular. Consider H2CO3, quote unquote, or true H2CO3, carbonic acid, or H2S, etc. Again, there are a number of examples in the acid-base table. Okay. Now, I'm not going to deal with this case because that's analyzed in the notes. You can read that. What you read about true carbonic acid in the notes at this stage of the game, where we are presently at. Did you read this stuff? Did you read how Ka for true carbonic compares to Ka for hydrated CO2? Did you read how much true carbonic you get when you bubble carbon dioxide in the water to make seltzer water? You're supposed to read this stuff. Well, in any case, I won't ask for a show of hands to find out who did and did not read this stuff. But read it. All right? So we're going to jump to this case. And then as necessary, we'll go back to that stuff. K equals Ka1 H2S equals 1.1 times 10 to the minus 7. 2. As with sulfuric acid solution, behaving in polyprotic fashion, we had to consider the ionization of HSO4 minus. Well, for polyprotic H2S, specifically diprotic, we also have to consider the ionization of HS minus. K is Ka2 H2S equals Ka HS minus equals a number. Now then, don't look at the acid-base table. I want you to tell me something about the size of this number. That's Ka for HS minus. Relative to Ka water. Ka water is 1.8 times 10 to the minus 16. I want to know something about the size of this number right here compared to 1.8 times 10 to the minus 16, which is Ka water. Bigger, smaller, same as. I got a strong feeling that we would all vote for not the same as. So let's go to bigger or smaller. I repeat, Ka water is 1.8 times 10 to the minus 16. How many vote that KaHS minus is bigger than 1.8 times 10 to the minus 16? I want votes. If I don't get votes this time, I'm writing the name of every non-voter, and you will be assigned a 0 for the course. Game is over. How about that for being damn mean? I mean damn mean. That's a half a vote. I want vote. I want yup votes. I want to see that you're standing up for what you think. How many vote that KaHS minus is smaller? How many didn't vote? I want to know where the zeros go. Okay. On the acid-base table, where do you find this thing? How much strong compared to hydroxide ion? This is a stronger base than hydroxide ion, isn't it? And hydroxide ion is a conjugate base of water, isn't it? Well, if this is a stronger base than the conjugate base of water, that guarantees that the conjugate acid of this base has got to be weaker than water as an acid. Right? Are we surprised at that? Hey, the negative charge density of this thing is enormous. That's why it hangs on to H plus so tightly. Because in order to make this by this reaction, you got to tear H plus from this thing. And that's a tough job. That's what Coulomb's law tells you. So, we'll now write the number down. It's only known to one significant figure. To my knowledge, I haven't seen it reported beyond one sig fig, because that's a daggone tiny number. And a number that small is hard to get by making measurements in the laboratory. And that's the only way you can get the number. I mean, when you start dealing with molarities that are so small, they give you K values like this, you're measuring concentrations that are mighty, mighty, mighty tiny. And that's not easy to do reliably. Okay? Now then, let's get at the main difference between the hydronium ion molarity for a solution like this compared to the other two cases. One of the cases we already looked at. Parin acid was molecular but strong, that's a sulfuric acid solution. And the other case we haven't looked at yet. That's a hydrated metal ion acid. This system, the parent polyprotic acid, is weak and molecular. Both things, weak and molecular. Gives us the simplest system with which to deal from an arithmetic standpoint. That's CY. There's our two equilibrium constant expressions written chemically. When you start putting in X's, they can't talk to you anymore. Question. This K value is small. But how does this small K value compare to this K value? This K value is 1 trillion times bigger, 10 to the 12th times bigger than this K value. Question. Do you think this second ionization, the second ionization, is going to contribute measurably to the hydronium ion molarity in H2S solution? No way. I mean, if for no other reason. You're not making this in water solution. We already talked about this. Okay? So here's why dealing with calculation of solution properties, specifically hydronium ion concentration, for a water solution of a polyprotic acid, which is A, weak, got a small Ka value, okay, and B, molecular, is that you only have to pay attention to the first ionization equilibrium, which means this can be treated as this. This applies. Parent polyprotic acid is weak and molecular. Well then, for this solution, 10th molar to 2 sig figs H2S, what's the hydronium ion concentration? I don't want to see any push buttons. I'm waiting. Time is a wasting. I'm still waiting. From now on, each second that I wait will cost each and every individual 10 points. 20,
21.
30, 40. We're going downhill fast. You don't have to raise your hand. Tell me the answer.
1.1 times 10 to the minus 4.
Close. 1.0 times 10 to the minus 4. But you just bail these people out. They each only lost 30 points. I'm giving you back the 30 points because you responded. That's rotten pool, isn't it? Dirty, nasty teacher. Ooh, you mean person. Woo. Where's this come from? You think for this solution, if m sub I is 0.10 and Ka is 1.1 times 10 to the minus 7, which is a small number, that I have to pay attention to x in the denominator to solve this? Were you asked about this on the exam? You betcha. Because I'm going after understanding, that's it. I don't care about taking numbers and shove them into the formulas and pushing buttons and getting answers that don't mean a damn thing. Because you didn't have to think about them. So, I wind up taking the square root of 1.1 times 10 to the minus 8. And there's the square root. Done. Now comes the next question. For this solution, what is the sulfide ion molarity? For starters, would you recognize that whatever it is has got to be awfully small because sulfide ion is such a strong base? What is it? I'll give you a clue. The numerical value for the sulfide ion molarity is on the board. What is it?
1 times 10 to the 19.
How about that? There it is. If the second ionization doesn't go anyplace, hydronium ion molarity and HS minus molarities must be equal, which is why this applies. Well, if these molarities are equal, then there's the sulfide ion molarity. Done. It's not magic. Okay? Now, before we go past this point, I'm going back to H2CO3, hydrated or true. Okay? If I have let's leave that stuff there for a moment. Time to time I get so excited about this and I erase stuff that I need not have to write again. And I don't like to do that. Okay. The quotes, of course, mean hydrated CO2. I take away the quotes, we're talking about true carbonic acid. Ka, true carbonic acid, is much, much larger than Ka this. The numbers are in the book. Here Ka is 4.2 times 10 to the minus 7. Here Ka, I think, is 2.4 times 10 to the minus 4, but I'm speaking from memory. It's in the book. Okay? Ka1. I'm speaking from memory on all of this stuff. I don't care. You're looking at the acid-base table, and you're looking at the information in those. This is 4.2 times 10 to the minus 7, right? Mm-hmm. And here, tell me what it is.
2.5.
2.5 times 10 to the minus 4? Yep. Well, that's terrible. I thought it was 2.4. I lose. So because I flunked that one, I'll give you back your 30 points. Isn't that nice? Okay. For these two solutions, same molarity. Two questions. How will the hydrogen carbonate ion molarities compare? I'm not asking for the value. You'd have to do some arithmetic to get the value. I'm asking how they will compare. Will the hydrogen carbonate ion molarities be the same for these solutions? If they're not the same, it's got to be greater in one of the solutions compared to the other. For which of these two solutions is the hydrogen carbonate ion molarity greater? And why? I'm listening. The ionization equilibria are identical, right? Except that in one case you're making hydrogen carbonate ion from true carbonic, in the other case you're making it from hydrated CO2. But other than that, the ionization equilibria are identical. You got quote-unquote H2CO3 plus water, double arrows, hydronium ion, and hydrogen carbonate ion. The other one, same equilibrium, except no quotes on H2CO3. But what's the difference for these two equilibrium reactions? Ka for true carbonic is a lot bigger than Ka for hydrated CO2. So So for which of these solutions is the bicarb concentration greater? Or is it the case the bicarb molarity is the same for each?
It's not the same.
What say you? For which solution is how do the bicarb molarities compare for these solutions? Speak up.
The HOCO2 minus,
Bicarb molarity.
it'd be greater in the true carbonic acid
Why?
because the Ka value is greater.
So?
You have a greater extent for creating
Yeah.
BL.
That's it.
Yeah.
Ionization extent for true carbonic exceeds the ionization extent for hydrated CO2. So the bicarb molarity has got to be greater for true carbonic. So I'll write greater for true carbonic. Now then, how about the carbonate ion molarity for each? You remember what we did over here? You have Ka1 for these acids on the board. I want you to look at the acid-base table and tell me what the value is for Ka2. You tell me and I write it down. Looking at the acid-base table? Well, come on, tell me.
4.8 times 10 to the negative 11.
Bingo. Isn't it Ka for bicarb ion? Because beside making hydronium ion, when those two parent acids react with water, also make bicarb ion. So Ka bicarb ion corresponds to Ka2 for both of these acids, be it true carbonic or hydrated CO2. So I go back to my question. For these solutions, what's the carbonate ion molarity? Now I want the value. After all, I just wrote the value on the board. It's 4.8 times 10 to the minus 11, isn't it? Did we not see here? After the H2S solution, the sulfide ion molarity is equal to Ka2? Because of this condition? Will a similar condition be reached? Does a similar condition exist in each of these two solutions? Does 4.8 times 10 to the minus 11 appear to be a number that's a whole lot smaller than either of these numbers? You betcha. That means the second ionization isn't going anyplace, just like that second ionization isn't going anyplace. I repeat, the reason why determination of solution property like hydronium ion concentration for a water solution of a polyprotic acid which is weak in molecular, you only have to pay attention to the first ionization equilibrium. Because the second ionization equilibrium doesn't go anyplace. I don't care what the weak paired polyprotic acid is. The second ionization equilibrium doesn't go anyplace. So the first ionization equilibrium, by application of x squared over m sub I minus x, always allows you to get the hydronium ion concentration. And this establishes that. The species produced when the parent acid doubly ionizes, when H2X becomes X2 minus, whatever X is. Okay. Carbonate ion, sulfide ion, who cares? The molarity of that X2 minus species is always Ka2. End of story. Now then, Why is it that the second ionization doesn't go anyplace? Why is it that the second ionization, when we have a parent acid that's polyprotic, weak in molecular, why is it that the second ionization goes no place? Why is it that Ka2 is so tiny? Compared to the first K value. For such an acid as this, we'll write the question down. Why is it that Ka1 much bigger than Ka2? And X2 minus equals Ka2. I told you what X2 minus is. Do you recognize that when we're dealing with a molecular acid? After it ionizes one time, do you have an anion or a cation? If H2X loses H plus, it becomes an anion. It's a negatively charged thing. So what you have to do, Coulomb, is pull a H plus from something that's negative. And that's not easy to do, is it? Now let's look at the two negatives of a specific nature for these two solutions. We know that for any H2S solution, the sulfide ion molarity, I don't care what the number label on the bottle is, it's Ka2. And for any H2CO3 solution, I don't care if it's true carbonic or hydrated CO2, the carbonate molarity is, for such a solution, always 4.8 times 10 to minus 11. But 4.8 times 10 to minus 11 is a hell of a lot bigger than this. And this is true because this is one heck of a lot stronger base than this. Now let's take a peek into the future. Why is this base a much stronger base than that base? Why?
It's more electronegative.
Huh?
For S2 minus, we're going to pick up a hydrogen more than CO3.
What do you think base strength depends on? Bronsted base.
The ability to pick up
What does the ability to pick up H plus depend on?
coordination.
Yeah, negative charge density. B, L, base strength. Depends on minus charge density. What else could it depend on? H plus is nothing but a positive charge. Hey, if H plus goes in the solution, it looks around for that thing that's got the greatest effective negative charge density. Bang, that's where it goes. I mean, this is monatomic with a charge of minus 2. This is tetratomic. Do you think this has got a negative charge concentration anywhere near this? Now then, on what bases can we argue that the negative charge density of this is a whole lot smaller than the negative charge density of this? The facts are that this is a species with a much greater negative charge density. It's a much stronger base. We want to know why. What analysis would you apply to carbonate ion to show that it has a much smaller negative charge density than sulfide ion? I'm listening. What structure? How about that? There's the Lewis structure for carbonate ion with formal charges applied. What valence electron property is exhibited by this ion? I'm listening. Resonance. Doesn't matter where I put the double bond because there's no double bond in this thing. Just like there are no single bonds. Each CO bond is equal length and strength. What is the bond order for a carbon-oxygen bond in this species? Bond order. Nope. 1 point, well, it's 1.33. Call it 4/3, right? Remember how to get bond order? You count up the number of bond sites you're looking at, 1, 2, 3. And then for that number of bond sites, you count up the number of bonding electron pairs at the bond sites. 1, 2, 3, 4. Take the number of bonding electron pairs total, divide by the number of bond sites. 4/3. So take note that the true formal charge for an oxygen atom, for carbonate ion, the true formal charge is what? True formal charge. True Fc for each O equals how much? I'm listening.
2/3.
Minus 2/3. How many oxygens do I have? 3. How much total charge do I have? Minus 2. Is that it? Hey, you can't beat structure analysis. That's what we're going to do. It's 1,000 times, 1,000,000 times. The most important property of any species is its structure. You want to know something about a species, you better look at its structure first and foremost. The answer might not lie there, but most of the time that's where the answer will lie. All right? So take note. You're looking at a species which has really a minus 2/3 negative charge on its basic atoms, because H plus can't bond to this thing for carbonate ion, and because of resonance. And furthermore, this minus charge is effectively stabilized because oxygen atoms are highly electronegative. Bingo. Pick it up from this point tomorrow.